everyone. Today we're going to start our look at momentum, and we're doing an exploration of momentum, and I'm very excited. I love this section, okay? But now where do we start? Well, let's have a look. Have you ever thought about why it is so difficult to stop a rugby player when they are running? Now, if you've ever watched a little bit of rugby, you'll know especially the big guys, like the ones who are in the lock and the scrum, they're very difficult to stop. And then if you listen, the commentators will use words like the rugby players scored a try because their momentum took them over the line. Or in a scrum, they'll go, the momentum of the scrum got them over the line. And you know what? As a science teacher, this is the one time when I go, actually, they got the term right. They used the right words, because often I have to be careful when I watch movies, because I go, oh, the science is bad. But it's all right. This one's not bad, because what they're referring to is how the rugby player's moving. So they're referring to motion. And we hear it a lot in sports, even with cricket. They'll say that the batsman used the momentum of the ball from the bowler, okay? Or in soccer, they don't use it very often, but in soccer, we get it so when there's a cross kick across the goal and one of the players headers the ball into the goal, he's using the momentum of the ball. So he's using the motion. So when we hear the word momentum, we conjure up the thought of movement. And that's what momentum's about. It's about the movement of objects, okay? So, this is what we're going to look at through this section, okay? We're going to look at the definition of momentum. We're going to look at the equation, because it's calculations. We're going to look at the properties. We're going to do Newton's laws in terms of momentum. We're going to look at how we change momentum, what the consequences of that are. We're going to look at conservation of momentum. There's lots of conservation laws that we're going to look at. Conservation of kinetic energy. And then we're going to look at impulse. Impulse has a lot of everyday applications to it. It's actually a really important section. Then we're going to look for today. Here are our keywords. First one is momentum. Okay, what is momentum? What does it do? What is it? How do we work with it? Then we're going to look at the term vector again, and I can hear the groans. Momentum is a vector, so it's a very important thing to look at, okay? Then we're going to look at vector diagrams with momentum. I can hear the groans again, okay? Vector diagrams are incredibly useful for us. So please don't go, well, I'm not in grade 11 anymore. Vectors aren't important. Vectors are very important, okay, because they help us understand how the motion works, okay? So let's look at the definition of momentum. Momentum has to do with the mass of an object and its velocity. Remember I said when we started this with rugby players that they talk about using the momentum, so they're talking about the motion. So in other words, an object has to be moving for it to have momentum. Movement means it needs a velocity, okay? So when we look at it, mass, oh, I need to be able to write on the board. Okay, there we go. So there we go. Mass. Oh, I was just going to write mass again. That's M. V is velocity. What we need to see here is that when we define momentum, it's the product. Multiplication means product. So we're going to use that word. So when we define it, we've got to be careful that we don't say momentum is the mass and velocity of an object. That doesn't make any sense. What are we doing with the mass and the velocity? Are we multiplying it? Are we adding it? Are we dividing it? So it's multiplication, okay? It is the product of those two together. Now let's look at the equation. The equation comes from the definition. All of our equations have something to do with the definition or law that we're looking at. So if you know the equation, often it means that you can get to the definition or the law. So our equation is this. Momentum is mass times velocity. Nu, that's momentum. Okay. Please guys, it is a lowercase p. Capital P means power. Totally different concept. Okay, so this is a lowercase p. You know m is mass and you know v is velocity. That gets us to the units, all right? And momentum is a little different to what you're used to because a lot of times everything has its own set unit. But what we do with the units with momentum is it comes from mass. Kilograms is mass. Meters per second from the velocity. So it's got a unit that's made up of the units of the things we use to multiply it by. Okay? Please, you must use the right units here. Okay? And it's nice and simple. So the equation's easy. Now we need to look at the properties. Okay? We're doing a lot of groundwork today. Properties, number one, it's a vector. What does that mean? So we have to remember that when we define a vector, it means that it has magnitude. Magnitude means size, and it has direction. So we have to be able to give the momentum a direction. So forward, backwards, north, south, east, west, left, right. The direction, the way we describe the direction is going to depend on the question, okay? So we've got to look at the question and describe direction the way the question describes direction. Also, just a side note, when you look at direction and you've got a diagram, just because the object looks like it's going to the right doesn't mean it's going east. Be careful, okay? Because the way we draw the north, south, east on a piece of paper, east looks like it's going right. But that doesn't mean it's going east. It could be going north. We don't know. If they describe the object going to the right as being to the east, then it's east. Okay, so be careful with that one. It's a bit worrying because you want to give a direction in terms of compass points, because that feels like a direction. But right, left, up, down, those are all directions. They all make sense. All right, so just be careful with that for me. All right. Oh, look, I've written over my stuff, but it's okay, we'll take that out. So let's take what I wrote out here. Because it's a vector, it can be represented by a vector diagram. So we have to remember what a vector diagram means, okay? A vector diagram is an arrow. It's an arrow of a specific length, where the length of the arrow gives me the size of the vector, and the arrowhead shows me the direction it's moving in, okay? So momentum's a vector, so we can give it an arrow, all right? When we get to change in momentum in a few lessons' time, this is where life's going to get a little interesting with our vector diagrams, okay? But it's all right. We can do this. It's not that difficult. You've done vector diagrams before. All right, now, next thing. Momentum is directly proportional to mass. Remember, that sign means directly proportional. And I'll write sideways on the board. So, what does directly proportional mean? It means that if mass doubles, momentum doubles. If mass becomes 3 times smaller, momentum becomes 3 times smaller. Be careful here that you don't go, if mass increases, momentum increases. That's true, but they increase or decrease by the same factor. Okay, that's very important. Momentum depends on mass. Okay, not the other way around. Mass is the important part. Also, momentum is directly proportional to velocity. In other words, if I double the velocity, I double the momentum. If I halve the velocity, I halve the momentum. And if we go back to our rugby player situation, our big rugby players like the Locks are hard to stop because they have a lot of momentum because of their mass, okay? Some of them can run very fast, but generally they're not as fast as like our fly half or the winger, who tend to be a little smaller, okay? They still have a lot of momentum because they can run really fast, okay? So even though they're smaller, they're faster, gives them a lot of momentum, okay? Same with a cricket ball. Cricket balls have a lot of momentum because even though they're small and they're only about 150 grams, they go very fast. If we look at our spin bowlers who can bowl a ball at like 150 kilometers per hour, heaven forbid, big momentum, okay? Very big momentum. All right, so what have we looked at in this section? The definition, the equation, and the properties. We're going to take a short break, and then when we come back, we're going to put it more into some more theory for you. Okay, so we'll take a short break. Welcome back. We're going to carry on with what we started before your short break. All right, so just to remind you, we are looking at momentum. We had a quick look at the definition, we had a quick look at the equation, and we had a quick look at the properties. Okay, so which object, so we have a question here, has more momentum? A big object moving slowly or a small object moving quickly? Now we've got to go, well, most of us will go probably the big object moving slowly, because in our minds, we have this picture that momentum means it's got to be fast, because we often hear we're gaining momentum, okay? Or when you think of something that's rolling down a hill, and you go, they gain momentum, and by that we mean they're going faster. Sometimes we'll use the momentum in terms of work. So maybe you're studying for an exam and you feel like you've gained momentum because you got a lot done. And then somebody disturbs you and you're like, oh, my momentum's finished. I'm going to have to just start again. Yeah, it's not quite the correct way of using the word momentum, but you're thinking about motion. So when we think of something moving slowly, we often think it doesn't have a lot of momentum. But this is where we've got to go, actually, momentum's not just dependent on the size of the object. It's also dependent on the velocity, okay? And we can't go, it's just dependent on velocity. It's dependent on the size. So when I look at this question and I go, the big object moving slowly or the small object moving quickly, I actually don't have enough information, because I need to know how big the object is and how slowly it's moving. I need to know how small the object is and how fast it's moving, because the two work together. They're not independent. And it's very possible that these will have exactly the same momentum. There's no reason why they can't. I need to know more information. I need to have values. Now, here When I talk about more momentum, I'm talking about the magnitude of the momentum. The direction doesn't affect the amount of momentum. So they could be going in opposite directions, and that's fine. That's a direction thing. It doesn't affect the amount of momentum that we have, okay? So this is a little bit of a trick question because I can't give a definite answer. There are too many bits of information I don't know, all right? So, definition. This is how we would write it out. The momentum of an object is the product. Remember I said that to you? It's the product of the mass and the velocity of the object. Please, you must learn your definitions. These are your easy marks in your exams, okay? And you won't get any marks if you go momentum is the mass and velocity of an object. Remember I said to you, you've got to give me product. That word product is very important. The equation, P equals mv. The nice thing is, given to you on your information sheet, lowercase p. So P is momentum measured in kilogram meters per second. Be careful here because we see this from time to time where you make that a big K. It's a lowercase k. So just be a little careful for me there, okay? M is mass measured in kilograms. This is a big one because we get a little confused sometimes. The SI unit for mass in physics is kilograms because we're dealing with stuff we can see and touch and feel and that sort of thing. In chemistry, it's grams, all right? So be careful here. We must work in kilograms. Velocity, meters per second. So that also means that you've got to remember how to convert because sometimes they're going to give you the velocity in kilometers per hour. Okay, so I'm just going to do a quick thing for you over here. To go from kilometers per hour to meters per second, you must divide by 3.6. This is just an aside. So this is just something you can keep as on a back burner somewhere, okay? Because it might come up in vertical projectile motion, it might come up in work energy and power, but you need to be able to convert that, okay? So we divide by 3.6. I'm not going to worry too much about how we get there. Then, momentum is directly proportional, we've spoken about this already, to the mass of the object, okay? We cannot describe mass as being directly proportional to momentum because mass doesn't depend on momentum. Momentum depends on mass, okay? So the bigger the mass, the bigger the momentum. But remember I said to you, they change by the same factor. If I make the mass 3 times bigger, I'll make the momentum 3 times bigger. If I make the mass 10 times smaller, the momentum becomes 10 times smaller. Generally speaking, in our calculations, the mass of an object will remain constant. Okay, it makes our calculations a little bit easier. But the mass doesn't always have to stay constant. There are definitely situations where mass doesn't stay constant, like a rocket lifting off to go to space. It uses up its fuel, which makes it lighter. Okay, so mass is changing. But for us, in normal, everyday sort of situations, we assume mass remains constant, okay? Just to make our calculations easier. Velocity, momentum, is dependent on velocity. So if the velocity changes, momentum changes, but again, they're directly proportional. So that means for us that they change by the same factor. If I make the velocity 3 times bigger, the momentum is 3 times bigger. If I make the velocity 2 times smaller, the momentum's 2 times smaller. But what I need you to get here is the velocity we're talking about is going to be constant velocity. we are going to ignore the brief moment in time when, if the velocity changes, there's acceleration. We're going to ignore that, okay? Because it makes the calculations very difficult. So we're going to look at situations where there's a velocity and then there's another velocity afterwards, but we're not going to worry too much about what happens in between at the beginning of this, okay? Because we want to keep it as constant velocity. So we're not going to look at situations which make it a little bit more real life. So for example, when you have an athlete running down a track, and say even Usain Bolt, who does the 100 meters in a ridiculous time, he doesn't run at a constant speed throughout the race. There's a speeding up as he starts the race, then he gets to a little bit of a constant velocity, probably speeds up again, or slows down. It all depends on the race. We're not going to worry about all those different changes. We would just assume that it's a constant velocity for the whole race. I know it's not completely real world, but we're just trying to get a concept across. We're trying to get the basic foundation of momentum. If you study physics further, then you'll do all the other stuff, because then you've got the maths as well, okay? So, momentum is a vector. We hate vectors, I know. It's all right, we're good. What does that mean? Momentum has a direction. We've spoken about that. And the direction of the momentum now is the same as the velocity's direction. So if the velocity is east, the momentum is east. It gets its direction from the velocity of the object. You can't tell me that an object that's moving to the left has a momentum to the right, because that just doesn't work, okay? Because momentum is about the velocity. So it's the same direction. And we can represent it by a vector diagram. So if I told you that we had a vector of 6 meters per second going east, and I wanted you to draw it as a diagram for me, what you would do is we have a line with our arrow, okay, and I put on it 6 meters per second. Now, I said to you in the last segment that we can't just assume to the right is east, and we can't. So I really need to be able to tell my examiner that I understand that that's north. Okay, so I know where the north is, and then that's east. You don't have to write the word east. Why? Because there's an arrow that's telling me it's going east. So just be careful with that one. Sometimes we want to put everything on there. We don't need to. Okay, the arrow direction tells me. I don't think, though it's not beyond the realm of possibility, that you will have to do these to scale, but you should be able to, okay? Also, if I'm drawing more than one momentum vector together, the relative sizes must be correct. So if I now tell you to draw a 3 meter per momentum, also going to the east, it can't be the same size line. So if it's 3, it should be about half the size. Now, I didn't measure them. I did it visually, okay? So when we mark something like this, we just look at it and go, it looks about right. We're not going to take out a ruler and measure it. But it's the relative size, okay? That still needs to make sense because they're vectors, okay? So, lots again. So we went through the definition, the equation, and the properties. That means we need to do problems, okay? Because that's all the theory. We need to do problems. We're going to do that in the next section. So make sure you got a calculator with you so you can do it with me. And we're going to take a short break, and I'll see you in a couple of minutes. Welcome back. Now now we're ready to get into the nitty-gritty and to do some calculations and see if what we've gone through has actually made sense to you. Okay, so remember, we've done the definition, we've done the equations, and we've done the properties. Now let's apply it. So here's our question. I want you to calculate the momentum, so it's a calculation, of a trolley. It doesn't really matter what the object is, really doesn't, with a mass of 7 kilograms, traveling 5 meters per second east. And then, so this is a two-part question, we're going to draw the momentum vector for our answer. Okay? So, let's start with the first part. With any calculation, it's important that you take out the information you need, because often, now this was quite a short question in the sense that there wasn't a lot of stuff around it and we're still in the beginning part, but when there's lots of information given to you in a question, you often get a little lost as to what goes where. So write a list, okay? And you saw when I started the question, the underlined words, do that as well, because then you get the important things, okay? So we have a mass of 7 kilograms moving at 5 meters per second. So my mass is 7 kilograms. It's going at 5 meters per second. And what do they want? They want the momentum. So momentum is mass times velocity, where mass is 7, velocity is 5. Now, I can do 7 times 5 because I like multiplication, okay, and it just works in my head. I'm pretty sure most of you can do 7 times 5 in your head. But in an exam, sometimes 7 times 5 becomes 25 or 23 or 30 because you're stressed when you do it in your head. So you know what? Use your calculator. So I have my calculator. Okay, let's just move it here a little bit. So we're going to go 7 times 5. It's 35. Okay? Please, there is no shame in using your calculator for these. I think there's more shame in not using your calculator because you don't want to look stupid and you get the wrong answer. Okay? Or, and I've seen this often, you go 7 times 5 and you give me 12 because you added them instead of multiplying them. Use your calculator. So we know it's 35, but remember, we've got to put in our units, and we've got to put in direction, and they told me it was going east, so my direction is east. Okay, we've done the first part of the question. We know that it's 35 kilogram meters per second east. Okay, and I'm going to draw the vector diagram on this one. Vector diagram, it's going east. Please use your rulers because that's not very straight. 7, no, see, this is why you've also got to check because it's not 7, it's 35. 35 kilogram meters per second. And I need to show that I know that that's east. So there's my north line. Okay? Straightforward. Nothing difficult about that. Let's add something to this or make it a little bit more difficult. So the 7 kilogram trolley is now moving at 10 meters per second east. So we have doubled the velocity. It was going at 5, now it's going at 10. How does its momentum compare to the momentum already calculated? So to the 35. Then they want us to calculate the new momentum, and they want us to draw a diagram representing the momentum. So let's start with the question, how does it compare? Please be careful here. They are not asking you to give the value. They're saying compare it. Is it bigger? Is it smaller? Is it the same? Okay. We could have also asked by what factor does it change? Okay, so we go back to the fact that we know momentum is directly proportional to velocity. The velocity doubled, so the momentum doubles, which means, how does it compare? It's now bigger. Okay? It's bigger. And what we can say, if they had asked us to explain our answer, which is possible, we would do this. We would go velocity doubled. So we say what happened, okay? Momentum is directly proportional to velocity. Oh, it's a big word. Okay. Therefore, momentum will also double. Now, the question didn't ask for an explanation. I've put an explanation so that you've got that in your notes and it makes sense when you look at it again. Okay, so it's just to help you when you go through this again at some stage. Then the same one, now they want us to calculate the new momentum. Only thing that's changed is this has become 10, so we know momentum is mass times volume, velocity. Okay, 7 times 10. Again, I'm sure you can do 7 times 10 in your head, all right? But exam conditions, we rather be safe than sorry. So, oops, get rid of that. 7 times 10. No, not 7 times 1. You've also got to put it in your calculator, right? Times 10, 70. Okay, so we know that it's going to be 70 kilogram meters per second. Direction hasn't changed, so it's also east. And they want a vector diagram. So remember I said the length of the arrow is important as well. The last arrow was quite small, so for 35. So now I've got to draw a bigger arrow because it's actually doubled. It's gone to 70. So I'm going to draw a longer arrow. 70 kilogram meters per second. And of course, we're going to indicate that we know where north is. Okay, straightforward. Not so bad. Did a nice comparison. Let's do another one. Now look what they do. A 2 kilogram block is now added to the 7 kilogram. By adding it, we are increasing the mass this time. Now, it's not an increase in mass where we doubled it. It's a funny factor, okay? But we've still increased the mass. But it's now still going back to the original velocity, which was 5. Okay, so we've taken the original situation and we're changing the mass. How does this momentum compare to the first momentum calculated? So it's not the momentum we calculated in the second question, the momentum we calculated in the first question. Calculate the new momentum, draw a vector diagram. Okay, well, let's start with the first part. 2 kilograms added to 7 kilograms. We've increased mass. Momentum is directly proportional to the mass. So if the mass increases, the momentum needs to increase. So that means for us that this momentum is bigger than the first momentum. So again, it's bigger. They didn't ask for an explanation, but we're going to put one in anyway, like the last one, because that means that when you come to study, you've got an explanation. You can understand what we did. So remember, the mass increased. Let's write it up properly. Let's do this. Okay, so, and let's put the G back there. Mass increased. okay? I can't put a factor here because to work out what the factor is, because it's going to be a fraction, we're not going to worry about that, okay? Mass increased, and then we should really go since momentum is directly proportional to mass, the momentum will also increase. Straightforward, not a problem, okay? That's the explanation type question. Now they want you to calculate it. So, first thing we need to recognize is my mass is now 2 plus 7. That was the big MB, okay? So now we've got 9 kilograms. Momentum is mass times velocity, so now I've got 9 times 5. We're going to use our calculators. Okay, 9 times 5, 45. So this one, and remember it's still going east, we haven't changed direction. This one is only a little bigger than the first one. Remember, the first one we calculated was 35. Now it's 45. But the mass didn't increase by that much. So we shouldn't expect a big increase in the momentum. But it does mean that when I draw this line, it must be slightly bigger than the 35, okay? And obviously smaller than the 70. So when we draw this one, okay, this is going to be 45 kilograms meters per second, and we need to know where the east is. Straightforward. We like this. This is nice. This part is easy, and as long as we get the calculation part in here and we understand the relationship between mass and velocity, we're going to be fine, okay, with momentum. So, what have we learned today? Momentum is the product of an object's mass and the object's velocity. Product of mass and velocity. The equation is P, little p, not uppercase, no, it's not a capital, which is mass times velocity. Its units, kilogram meters per second, which of course you know come from there, so it's one you can work out. And momentum is a vector. Remember, vector means that it has size and direction. Okay, and I don't think I put, yeah. And momentum, because I've written over there again, because, you know, momentum can be represented by a vector diagram. And what I didn't add into the summary is this. So let's just put it in on the side, okay, is that momentum is directly proportional to mass and momentum directly proportional to velocity. They like questions where you've got to look at the relationship between things, okay? So, we did a lot today. We did the definition, we did the equation, we did the properties. I think you can probably sense where we're going in the next question, which is going to, next session, it's going to be Newton's laws. But that's where we're going to stop for this lesson, and I will see you again next time.